Hello and welcome back to this series discussing the stiffness method. In this session, we will complete the stiffness method for a truss. So after finding the displacements, we will move on to find reactions and internal forces in a truss example. This will complete the stiffness method for analysing trusses. So far, we've used the stiffness method to build and solve the equation KD equals F, giving us the displacements of every node in the structure. In this lecture, we'll complete the picture. We'll calculate the support reactions that keep the structure in equilibrium and the internal forces carried by each element. We'll demonstrate all of this using a truss example, which we'll first solve by hand and then code. Everything in the stiffness method comes back to this equation. It simply says that the total force at every degree of freedom equals the stiffness of the structure multiplied by the displacement at that point. Every step we've done so far, assembling the element matrices, applying transformations and adding loads, was to create and solve this one relationship. Once we've assembled the global stiffness matrix, we recognize that not all degrees of freedom behave the same way. Some are restrained, for example at a fixed or pinned support, and their displacements are already known or prescribed. The rest are free to move under load, and their displacements are what we solve for when we compute D. To handle this properly, we partition the full stiffness equation into blocks that correspond to these groups. Each block tells part of the story. KRR relates how the restrained degrees of freedom interact with one another. The stiffness felt directly at the supports. KRF and KFR describe the coupling between the restrained and free nodes, how movement in one part of the structure causes forces in another. KFF captures the stiffness relationships among the free degrees of freedom themselves. On the right hand, we separate the applied forces FR and FF. But there's one more ingredient, the reaction vector R. Reactions appear only at the restrained degrees of freedom because those nodes can't move. If you think of the structure trying to deform under load, the reactions are equal and opposite forces at the supports that stop the motion. This partitioned form makes it easier to isolate the unknown quantities. We can first solve the lower set of equations for the free displacements dF, and then return to the upper set to find the reactions R. Let's demonstrate this equation, which shows the global stiffness matrix for a truss structure. We can tell it's a truss because the displacements at each node are labelled with U and V, representing horizontal and vertical movement. Each node, therefore, has only 2 degrees of freedom, one in the x direction and one in the y direction. For this particular example, the boundary conditions restrain displacements at nodes 1 in the horizontal and vertical directions and node 3 in the horizontal direction. That means that U1, V1 and U3 are fixed and equal to 0, while the remaining degrees of freedom are free to move under the applied loads. We'll see how the stiffness matrix is partitioned according to these restrained and free displacements. First, we cross out the restrained degrees of freedom with red lines. This allows us to clearly see the restricted and free areas. Orange boxes appear around KFF. This block is the most important one. It contains the stiffness terms that relate the free displacements to one another, and it's the portion we use in the main reduced equation KFF multiplied by DF equals FF. Once the boundary conditions are applied, this is the matrix part that we solve to find the unknown nodal displacements. The red boxes highlight the members of KRR. Because those displacements are fixed at 0, this part of the matrix won't appear in the reduced equation that we actually solve. Purple boxes highlight the members of KRF. This block couples the restrained and free degrees of freedom. It becomes important again when we calculate the support reactions using the expression R equals KRF multiplied by DF. Grey boxes appear around KFR. This is the complementary relationship and shows how the free nodes are influenced by any potential motion at the restrained ones. Altogether, these 4 coloured blocks represent the fully partitioned global stiffness matrix for the truss. And once boundary conditions are applied, only the KFF portion is used to find displacements. The other submatrices are used afterwards to recover the reactions and verify equilibrium. When we partition the global stiffness matrix, its rows and columns are grouped according to restrained and free degrees of freedom. The number of restrained degrees of freedom is NR, and the number of free degrees of freedom is NF. The four submatrices KRR, KRF, KFR, and KFF follow directly from that count. On this slide, you can see the sizes of these submatrices and of the restrained and free parts of the displacement and force vectors. Now that we've partitioned the global system, let's focus on the restrained rows. These correspond to the supports. At these points, displacements dr are known. They're usually zero, so the unknown quantity is the reaction force R. If we just take the top part of our partitioned equation, we have KRR times dr plus KRF times dF equals KFR plus R. This expresses equilibrium at the restrained degrees of freedom. The internal stiffness forces on the left must balance both the externally applied load and the reaction force on the right. To isolate the reactions, we can simply rearrange the equation. If the supports do not move and have no load directly acting on them, the formula reduces neatly to R equals KRF times dF. That's the version that you'll most often see, and it's the one we'll use in our 3-bar truss later. Despite what I said about using the smaller equation, let's just unpack what each part of the bigger expression means in real structural behavior. And this is just in case you need that for any work that you're doing. The first term, KRR times dr, accounts for cases when a support does actually move. So imagine a foundation settling or bearing shifting slightly. Even the tiny movement will mobilize stiffness in the structure, generating a reaction force which will be proportional to dr. So if the support moves downwards, for example, the structure will push upwards in response, and that push will appear here. The second term, KRFDF, is the one we use most often, as we said, and it captures the way the deformation of the free nodes, so the parts of the structure that move under the load, push or pull on the restrained nodes. Think of it as the structure's internal feedback. As the loaded joints move, the support feels that movement through the stiffness connections between them. The third term, minus FR, simply subtracts any external forces that are applied directly at the support. So if a load was already pushing on the support, we don't want to double count it as a reaction, so it's taken away from the calculated total. As a result, R is the true reaction force. It's the exact magnitude and direction that the support must provide to keep the structure in equilibrium. This equation is powerful because it tells us that we never need to guess the reactions. They're an automatic byproduct of solving for displacements. And once we have the displacements, the reactions follow naturally. Once we know the overall displacements, we can zoom in on each element to see what's happening inside it. Every member must stay in equilibrium with its own deformation, and that relationship is simply written as K times d tag. D tag describes how the element's two ends have moved relative to each other, and multiplying it by the element's stiffness gives the internal forces developed along its length. These are the axial or bending forces that the element carries to keep the structure stable. So just as K times D equals F describe the equilibrium for the whole structure, K times D tag equals F tag describes one equilibrium for one individual element. And we have seen this before when we moved from the element stiffness to the global stiffness via the transformation matrix. You might remember this relationship for lecture 5 when we introduced the transformations for a truss element. At the time, we used the symbol U for displacements. It's the same quantity we now call D. Each element has its own local coordinate system aligned with its axis, while the global system is common to the whole structure. To move between them, we use the transformation matrix T, which is made up of cos theta and sine theta. Earlier, we used the transformation matrix T to rotate the local stiffness matrices into the global system for assembly. And now we're using the same transformation in reverse. T converts the global displacements to local displacements before calculating internal forces, and T transpose converts the resulting local forces back into the global system. So the transformation works in both directions. It's the bridge between the local behavior of an element and the global behavior of the whole structure. And this allows us to use the results we already have to find the local member forces. Before we move on to a truss example, let's quickly summarize the full procedure. Once we've solved k times d equals f and know all the nodal displacements, we're ready for the two final steps. Step 1, we recover the reactions at the supports using the restrained part of the stiffness equation. This gives us the forces each support must provide to keep the structure in balance. Step 2, we then find the internal forces in each element. We extract the nodal displacements, transform them into the local coordinate system using the transformation matrix, and multiply by the local stiffness matrix K. This will give us the axial, or bending in a beam, forces within the element. If we want to then move on to check global equilibrium or plot diagrams, we can rotate them back using the T-transpose. And finally, we confirm that the element end forces are equal and opposite, and that the total reactions and loads balance. A good numerical check that everything is consistent. This is the process that we'll now follow step by step for the 3-bar truss we've met earlier. So let's move on to look at this practical example of how the stiffness method is applied in full. We'll return to the same 3-bar truss that we used earlier when we introduced the transformation matrix. In this example, the truss members use E equals 200 gigapascals and an A of 1 times 10 to the minus 4 meters square. These values are representative of a small steel bar in tension, strong, lightweight, and linearly elastic. However, such slender members in reality would buckle very easily if they were placed in compression, so in a real structure they would only be used in tension or combined with bracing to provide stability. In this example, we'll also provide a horizontal load of 10 kilonewtons at the top joint and examine how the truss deforms and the internal forces that develop in each member. This will allow us to verify the numerical process and then the physical interpretation of the stiffness matrix. Before moving on, here's the global stiffness matrix that we built in Lecture 5. Each term already includes the effects of element orientation through the cosine and sine components, all scaled by EA. It's a great reminder that we've already done the hardest part, which is assembling the structure's stiffness in global coordinates. Before we introduce supports or loads, this is the complete stiffness relationship for the 3-bar truss. The global equation F equals K times D. Next, we'll apply the real physical conditions, the supports and external loads, to reduce this to a solvable form. Let's start by adding the external forces. At node 3, we apply a horizontal load of 10 kilonewtons to the right. That means that F3x equals 10,000 newtons, and all other external forces are 0. This gives us the global load vector on the left-hand side of our F equals KD equation. Now we'll bring in the supports. The pin at node 1 prevents movement in both x and y, so U1 and V1 equals 0. The roller support at 2 prevents only vertical movement, so V2 equals 0. When we impose these conditions, the corresponding rows and columns in the global stiffness matrix no longer contribute to the solution. These displacements are fixed. By crossing them out, we isolate the smaller system of equations that involves only the free degrees of freedom. The remaining degrees of freedom are free, and the corresponding 3x3 submatrix that links them is what we call KFF. And that leads to the system that we solve next. KFF times DF equals FF. Now we can solve the reduced 3x3 system directly. Substituting the values for EA and applying the load gives us U2 equals 0, U3 equals 10.5 millimeters, and V3 equals minus 2.7 millimeters. These are small realistic displacements for a steel truss of this size and stiffness. Physically, the top node, node 3, moves to the right and slightly downwards under the horizontal load, while the roller's horizontal displacement at node 2 is negligible. This is our first key result, the deformation that drives both the reactions and the internal member forces. Once the free displacements have been determined, the reactions at the restrained degrees of freedom can be recovered directly from the partitioned form of the global equilibrium equation. In our case, the support displacements are 0, and there are no external forces acting on the restraints. So we can use the simple R equals KRF times DF. We can now use that expression to evaluate numerically for our truss. Here, the matrix shown is the KRF block. It links the restrained degrees of freedom, so the supports, with the free degrees of freedom, the moving nodes. Each coefficient expresses how a unit displacement at a free joint generates force at a restraint. We can substitute the solved free displacements from the previous slide and multiply by EA. Carrying it out gives us the support reactions. R1x equals minus 10 kilonewtons, R1y minus 13.33 kilonewtons, and R2y plus 13.33 kilonewtons. Physically, this means that the pin at node 1 resists the entire horizontal force with a 10 kilonewton reaction to the left. Vertically, the pin and roller form an equal and opposite pair of 13.33 kilonewtons, keeping the structure in vertical equilibrium. The results confirm global balance. The sums of horizontal and vertical forces are both zero. These reactions now close the external equilibrium and are the foundation for determining the internal member forces that follow. We already used the transformation matrix T earlier to convert local element stiffness into the global coordinate system. Now we use the same matrix in the opposite direction to transform the global nodal displacements back into the local element deformations. Multiplying by the local element stiffness gives the member end forces F tag. For a truss element, the first entry F is the axial force at the I end, and the second is the equal and opposite force at the J end. Let's apply this for two members of a 3-bar truss. We'll start off by calculating the axial force in member 2, which is the vertical bar between nodes 2 and 3, using the full transformation matrix formulation. At the top left, we start with the transformation matrix T2. Because the member is vertical, its direction cosines are C equals 0 and S equals 1, so the transformation simply extracts the vertical displacements of the two nodes. Next, we write the local stiffness matrix, knowing that L equals 4 meters. Below that, we can form the element displacement vector from the global displacements. We only need to take what happens at nodes 2 and 3. And finally, we can apply the stiffness method. F2 equals K2 times T2 times D2. Carrying out this multiplication gives end forces of plus 13.3 kilonewtons and minus 13.3 kilonewtons. We can compare that to our sign convention, which easily lets us see that the element is in compression, with the top joint being in minus and pushing downwards, and the bottom joint pushing upwards. The diagram you can see on the right confirms the behavior. The loaded joint moves slightly downwards, shortening the vertical bar, and the diagonal member takes the corresponding tension. So for member 2, we obtain N2 equals minus 13.3 kilonewtons. We can repeat the same process for member 3, which is the diagonal bar between nodes 1 and 3. At the top left, the transformation matrix T3 includes both the cosine and sine of the member's inclination, just as we previously developed it. The local stiffness matrix again has the familiar truss form, and we can substitute EA and the length of 5 meters. The element displacement vector comes from nodes 1 and 3 this time. Since node 1 is pinned, its displacements are 0, and node 3's values come directly from the solved results on the previous slides. When we perform the matrix multiplication F3 equals K3 times T3 times D3, we obtain end forces of minus 16.7 and plus 16.7 kilonewtons. And looking at our sign convention, this means tension. The diagonal member is being stretched. On the right-hand diagram, you can see this easily. So for member 3, N3 equals plus 16.7 kilonewtons tension. And on this slide, we can see a summary of everything we found in the worked example. A 10 kilonewton horizontal load was applied at node 3, and the structure responded with small realistic displacements for a steel truss of this scale. The top joint moved about 10 millimeters to the right and dropped about 2 to 3 millimeters vertically. This behavior is what we would expect for a light truss under a moderate horizontal load. The support reactions balance the applied load exactly. The reaction of 1Rx of 10 kilonewtons acted to the left, and R1y was 13.3 kilonewton acting downwards, and R2y 13.3 kilonewton acting upwards. Both horizontal and vertical equilibrium were perfectly satisfied. Internally, the diagonal member between nodes 1 and 3 carried 16.7 kilonewtons in tension, and the vertical member between nodes 2 and 3 carried 13.3 kilonewtons in compression. The bottom chord between nodes 1 and 2 carried almost no force, as expected from a zero-force member. The results confirm that the structure deforms and reacts exactly as expected, and this completes the full stiffness method workflow. And now that we've completed the worked example, let's take a moment to step back and review the entire method. We started by assembling the global stiffness matrix and load vector. This combines the stiffness of each element already transformed into the global coordinate system. Next, we apply the boundary conditions by enforcing the supports. We then solve for the nodal displacements. And once these are known, the rest of the problem unfolds naturally. With the free displacements in hand, we can solve the reactions, which in our case simplified neatly to R equals KRF times dF, and those reactions ensured equilibrium at the supports. Finally, we can compute the internal member forces. In a truss, from these we can identify if a member is in tension or compression and verify that the structure is in equilibrium. The key point is that the stiffness method links loads, displacements, and internal forces through a single consistent matrix framework. The same matrices are used twice, once to assemble the global stiffness and once again to recover the internal element forces, which makes the method elegant and easy to automate. It's a clear step-by-step sequence that translates perfectly into code, and that's exactly what we'll do next. So having established the full theoretical basis, we are going to turn our gaze onto implementation. We'll translate the full procedure into a short MATLAB or Octave script using the truss example we discussed here. As I mentioned earlier, the goal is not to become programmers, but to understand each theoretical step and how it corresponds to a line of code. We will quickly look through what we've coded in previous lectures, focusing on the final steps, solving the stiffness equation and finding the displacements and reactions and internal forces. If you'd like a full line-by-line explanation, you can review the earlier coding sessions. We start off by setting up a clean script using clear, close all, and CLC. The header reminds us that this is a 2D truss using the stiffness method, axial deformation only, with U and V at each node. All inputs and outputs are in SI units, so the forces are in newtons, lengths in meters, and stiffness in newtons per meter. The next few slides will look familiar. We'll go through them very briefly, and if you need a full recap, just revisit the earlier lectures where we built these sections in detail. Here we define the geometry and connectivity of the truss. The node coordinates set out the position of each joint, and the element table shows us which nodes each bar connects. Each node has 2 degrees of freedom, U and V. The script then counts how many nodes and elements there are and automatically assigns the correct degrees of freedom number for each node. Here we define the material stiffness and cross-sectional area for the truss members. The modulus of elasticity E is set to 200 gigapascals, which is typical for steel, and the area A represents a 10 by 10 millimeter square bar, converted to square meters. Both E and A are applied to all elements using ones, meaning that every bar has identical properties, but this can easily be adapted if different elements have varying cross-sections or materials. This section calculates the geometry of each truss member, its length and orientation. For each element, we extract the start and end node coordinates and then find the horizontal and vertical projections, dx and dy. The element length is found using Pythagoras, and the direction cosines describe the angle relative to the x-axis. The values are stored for later use when we build the transformation and stiffness matrices. The angle is saved in radians, ready for conversion to degrees when printing the results. Each truss element carries only axial forces, so its local stiffness matrix is the familiar 2x2 form. The code loops through all elements, taking E, A, and L from earlier steps, and stores each element's local stiffness into a 3D array called K-local. This represents the stiffness in the element's own coordinate system before any rotation into the global axes. Each element's local stiffness matrix, K-local, must be rotated into the global coordinate system. For every element, the code extracts the cos and the sine of the angle and forms the transformation matrix. The global matrix is then calculated using the T transpose K and T, and the transformation matrix T is saved for later use when we recover the internal forces. In this step, we combine all the element stiffness matrices into one global stiffness matrix K. For each element, the corresponding node numbers are extracted, and the degrees of freedom are identified in the vector EDOFs. The element stiffness is then added to the correct positions of K, gradually building up the complete structure stiffness matrix. In this step, we create the global load vector for the truss. You've already seen this process when we worked with frames. It was more complex there because beams can carry distributed loads and moments. For trusses, it's simpler. Loads act only at the nodes and only as forces in the global directions fx and fy. The first line, F equals zeros, creates an empty global load vector sized to the total number of degrees of freedom. The next line defines the nodal loads in table format. Node, then fx, then fy. In this example, nodal loads equals 3, the node 3, 10e3, the 10 kilonewton horizontal load, and 0, because there wasn't any vertical load. There's also a safeguard line, and that checks whether the variable nodal loads exists. If not, it creates an empty one to avoid errors. The following for loop then assembles nodal loads into the global vector f. For each entry, the node number is read and its fx and fy components are extracted. These are then added to the correct positions in f using the degree of freedom mapping n and d1 for the horizontal displacement u and n and d2 for the vertical displacement v. This way, if multiple loads act on the same node, they are automatically summed, and the final vector contains all the nodal loads expressed consistently in global coordinates. Here's the resulting global load force F for our example. Only degree of freedom 5 has a non-zero value, which corresponds to the horizontal load at node 3, where 10 kilonewtons were applied. All other entries are 0, as no other nodes carried external loads. In this step, we apply boundary conditions and solve the global stiffness equation to find the nodal displacements. The example shows the truss we solved, which is supported by a pin support at node 1 and a roller at node 2. And this means that U1, V1, and V2 are all equal 0. This gives us 3 restrained degrees of freedom in total. These are listed in the array fixed DOFs as N11, N12, and N22. In our example, we could see what this leads to. The total number of degrees of freedom is generated as all DOFs, 1, 2, and DOF total. And then the free degrees of freedom are identified by subtracting the restrained ones using setDiff. This automatically calculates the free degrees of freedom, which looks like this in our example. Next, the global stiffness matrix and load vector are reduced to the free degrees of freedom only using KFF and FF. This results in the smaller linear system KFF times DF equals FF, which we can solve in MATLAB with the backslash operator. The backslash efficiently performs matrix division to compute the displacement vector for the free degrees of freedom. After solving, we can reconstruct the complete displacement vector, including zeros for the restrained degrees of freedom. The line D creates a full vector of zeros, and D free DOFs equals DF inserts the solved displacements in the correct locations. Here we can see how the final displacement vector, D, would look for our example. The zeros correspond to the restrained degrees of freedom at nodes 1 and 2, while the small non-zero values represent the displacements of the free node, in this case node 3, which moves under the 10 kilonewton horizontal load. Once we've obtained the nodal displacements, we can calculate the support reactions using equilibrium. The command RAll equals Kd minus F multiplies the global stiffness matrix by the displacement vector and subtracts the external load vector. The next line, rsupport equals RAll for fixed off, extracts the non-zero entries, giving the reaction forces at the supports. Here we can see the full vector RAll for our example, with zeros at the free degrees of freedom and the expected non-zero reactions at the restrained ones. These reaction values should balance the external loads, confirming that the structure is in equilibrium. We can see here at node 5, due to rounding errors, there is a teeny tiny reaction force, which obviously is a 0 in terms of the reactions. In this step, we calculate the axial forces within each truss member. These are found in the local coordinate system, acting along the element's own axis. The code begins by creating 2 storage variables, NLM, which will hold the axial force for each element, and FLOCALL, which stores the full local end forces N1 and N2 for reference. The loop then goes through each element in turn. For the current element, we identify its start and end nodes and collect the corresponding global degrees of freedom using EDOF. The displacement values from the global vector d are then extracted with d equals d for EDOF. Next, the global displacements are transformed into local coordinates using the stored transformation matrix. This gives the local end displacements for that member, how much each end moves along its own axis. We can then calculate the local end forces using F_loc equals K local times UL. This gives a 2x1 vector of axial forces at each end, equal in magnitude and opposite in direction, and these are stored in F_loc all. The internal axial force for the element is then recorded as NLM equals F_loc, taking the second end as positive tension by convention. Here we can see the resulting NLM vector, which lists the axial force in each element. Positive values indicate tension and negative values represent compression. These results show exactly how the structure carries the applied 10 kN load of our case, with some members stretching and others shortening to maintain equilibrium. And in the final step, we display all the key results from the analysis in a clear, structured format. The command format short-eng switches MATLAB to engineering notation. We then print each group of results in sequence using fprintf for headings and disp to display the numerical values. The script first outputs the global stiffness matrix and then displays element lengths and angles, which can help us verify the geometry is being computed correctly. Next, the global load vector F is printed, followed by the nodal displacement vector D, which shows how much each node has moved under the applied load. The support reactions are then displayed, with a note that positive values indicate forces acting on the supports in the structure. Finally, the script reports the element axial forces. One line per element showing the element number, its start and end nodes, and the axial force N with tension taken as positive. This summary neatly brings together the complete picture of the structural behavior. And here you can see how the last part of the results will appear in the command window. Although we've shown this code in MATLAB, it will also run directly in GNU Octave, which is a free open source alternative. Octave uses almost exactly the same syntax as MATLAB, so you can copy and paste this script and it'll work without changes. And that's us concluded how to use the stiffness method for solving a truss. In the next session, we will complete the stiffness method for solving beams and frames. We're nearly there, we've already found the displacements. We are just left with finding the reactions and the internal forces. So join me for that and the conclusion into this series.